Hello, learners of mathematics. Welcome to session 4 of unit 6 in the course Introduction to Abstract Algebra. In the previous section 3, we look at finite and infinite groups as well as subgroups. In this section 4, we are looking at ranks and their elementary properties. I am Mukaila Dasmani, your course instructor. By the end of this session, you should be able to explain what a rank is. Give at least 2 examples of a rank. Give at least 1 example of an unrank and state and prove at least 2 basic properties of a rank. Okay, definition of ranks. A rank is an algebraic structure, and that is real number with multiplication and addition. Real numbers where multiplication and addition are defined. That is, let me underline that one here. Real numbers with addition, multiplication defined. Okay, consisting of a set R together with 2 binary operations. So the first one is addition, and that is first operation, and the third one is multiplication, A plus B. So such that the axioms that are following in the previous sessions are hold. So when these axioms are hold and this 2 binary operation on real number plus and multiplication hold, then we say that that set is a ring. So this condition must satisfy, and first is addition on real number is an abelian group. And when addition on real number is a abelian group, what do we say? Then this axioms must be satisfied. The first is that 1 or I, you can say that closure property must define. And how do you define for all A, B, be a member of R? Then one can say that A plus B is also a member of R. So that is addition. Once addition is defined, once you add them, it must be closed. Also, the second one is commutativity. A plus B must be equals to B plus A. Then we say that the commutative property hold commutativity. Okay, and then also associativity should also be defined. Associativity should also be defined. A plus B plus C equals to A plus, let me clear that and make the last one that A plus B plus C. Okay, so for all A, B, and C being a member of R, great. Then we can have our fourth axiom, that is additive identity. Additive identity. So A plus the additive identity, A plus its identity the same, that identity plus A, and answer is A. Don't forget about the identity element. And then we also have additive inverse. So when you have A plus its inverse, it might be equals to the identity element. And here the identity element is 0. Okay, so identity element for addition is 0, and therefore, so you can say that the inverse is negative A. So that the first one hold is an abelian group. Then these 5 axioms are defined. Also, the real number under multiplication is a semigroup. So that's R, dot real number under multiplication is a semigroup. So when we say it's a semigroup, then we can say that for all A, B, and C be a member of R, be a member of the real number. So in the semigroup sense, we can say that the closure property hold. And what do we say? AB, that is A dot B, that is 1, is a member of R. Then we can say that the operation is closed under the set of multiplication. And then secondly, we can also have associativity. And how do we define A dot B dot C equals to A dot B dot C, that is multiplication, is also defined, and here associative is also defined. So when this condition is held, then the last of its kind that satisfies the definition of the rank is multiplication is distributive over addition. multiplication is distributive over addition. So here we may have right distribution or left distribution. For instance, we have A dot B plus C. A dot B plus C, or start a dot, not minus, because of the marker. Try to make it bold. A dot B plus C is actually equal to A dot B plus A dot C. Okay, so we call this one left distribution. Left distribution. You can see where the A dot is in the left hand side. And then we can also have other one, A plus B dot C. You can see where the multiplication is right hand side, and that is A dot C plus B dot C, and that is right distribution. Right distribution. Okay, so thank you for that, and let's proceed. Let's see example 8. Okay, you don't have example 8 here. Let me try to give you some of the example 8. Example 8, consider the system z plus. So we say that the integer z with addition defined on it, addition under the set of integer, forms an abelian group. Then I think you agree with me. Why? Explain. So this form an abelian group. That is example 1. Also, that is, we also have integer with respect to multiplication. Multiplication and define an integer with e equals to 1 is also semi-group. So explain why and then proofs. Okay. So therefore, in conclusion, we can say that integer with multiplication plus and dot forms what we call ring integer. So the two binary operations are defined. Addition is defined, multiplication is defined on the set of integers. Then we say it's a ring integer. Okay, so the next one is, let's say B. We can also have real numbers where multiplication and addition is defined. This one is multiplication. Let me clean that. Okay, multiplication. So the set real number where are the set real numbers. So this one is actually a ring. You can see that for real numbers, addition is defined, multiplication is defined. Then you can see it's a ring. So why proof? Also, you can also talk about the set of integers. Sorry, the sets of rational numbers with addition and multiplication defined. With addition and multiplication defined. Okay, and the last one maybe I want to talk is, let's say I can also talk about the complex numbers. Don't forget about the complex numbers. With addition, multiplication defined is also a ring. So try to explain you some numbers to prove. That will make you so easy understandable. Okay, we can't do all that because we want to shorten the video. Elementary theorems on rings. Elementary theorems on rings. So the first one is that if addition and multiplication under the set of real numbers is a ring, then the following properties are valid, and that is actually true. So the first one is that for every element in R, A dot 0 equals 0 dot A equals to 0, and that becomes the identity element. Okay, so don't forget about identity element and the addition. Okay, so let's see how to prove this one, and then maybe you can prove the rest because we don't want to make the video too long. So if I want to prove this one, you know that 0 is an additive identity, and if you agree with me, so we can say that A dot O is actually equal to, or let's say A dot O plus, let me start with that to become so simple. A dot naught plus A dot 0 is the same as, what do I get? I think I'll factor A out, right? 0 plus 0. You agree with me? Okay. And it's the same as A dot 0 because A plus 0 is actually 0. It's very interesting. And this is the same as A dot 0 plus 0 because 0 plus any number is the same as 0 and the number itself. So this looks something like very funny but very interesting. We can actually use to do something interesting. So therefore, what can we say? You can say that A dot 0 is actually 0. And you agree with me? And that is what we call equation 1. Let me say equation 1. That's left cancellation law. You see, very interesting. Okay, let's also check another one. Also, if I have 0 plus 0 dot a, what do I get? 0 plus 0 dot a. I can actually factor the what do you call it? 0 out. Oh, sorry, it's not 0 plus 0 dot a. Okay, so 0 dot a plus 0 dot a, rather, that's what I want to write. To look like the first one, I'm using the opposite one. So 0 dot a plus 0 dot a is actually equal to, you can factor it out. Okay, so you get 0 plus 0 dot a, and I think you agree with me. Like that, it doesn't change anything. Okay, so this is the same as, so this is equal to, let me continue from here so that it can go. You can see the same as 0 dot a as we did in the first section, and the same as, it's very interesting, 0 dot a plus 0 dot a. Okay, yeah, if I say 0 dot a, I can say plus 0 dot a, the same thing, nothing changes. Okay, so once that is satisfied, then we can say that this is the same as 0 dot a or 0 plus 0 dot a, and I think you agree with me, and the same as 0 dot a plus 0 dot a. It doesn't change anything, so therefore 0 equals to 0 dot a. Okay, and that is by the right cancellation. It will cancel by the right cancellation. So we get that. Therefore, we conclude that a dot 0 equals 0 dot a equals 0, and that is actually defined. So very interesting. Just, you can do this. You can play over this, and very interesting. So we have this theorem 8. For all a, b in R, a dot b minus b is equals to this, and then I and I are true. So you can just go through this, so simple, and then by using the cancellation laws and the inverse laws, you can make it so simple, and then you prove for that.